So let's review the unit circle definition of trig functions a little bit. Right over here, I've drawn a unit circle. And when we say unit circle, we're talking about a circle with radius 1. So for example, this point right over here is the point 1, 0, x is equal to 1, y is 0. This point is the point 0, 1. This is the point negative 1, 0. And this is the point 0, negative 1. That the radius over here, the distance from the center of the circle, which is at the origin, to any point in the circle, or any point on the circle, I should say, this radius is equal to 1. So the unit circle definition of trig functions leverages this unit circle. That's why it's called the unit circle definition. And we saw that if we define an angle as the kind of bottom side of the angle being along the positive x-axis, and then the other side of that angle, thinking about where it intersects the unit circle, so let's say that this is the angle theta, we define sine of theta and cosine of theta, or cosine theta and sine of theta, as the x and y coordinates of this point at which this side of the angle, the side that is not the positive x-axis, where that intersects the unit circle. So for example, this point right over here, if we would call this the x-coordinate of this point, so this value right over here, we would call that cosine of theta. We would call that cosine of theta. And the y-coordinate of that point, which is this point right over here, we would call that sine of theta. And in previous videos on the unit circle, we talked about why this is really just a natural extension of the SOHCAHTOA definition. What's useful is it starts to work for negative angles, it works for angles, it even works for 90-degree angles, it works for angles more than 90 degrees, it works for angles less than 90 degrees. So it's really, really, really useful. But what I want to do is leverage what we already know about the unit circle definition of trig functions to help prove the Pythagorean identity. And it almost falls out of the fact that this point right over here is on a circle of radius 1. So what is the equation of a circle with radius 1 centered at the origin? Well, the equation of that is x squared. We have other videos where we really prove this using the distance formula, which is really just an application of the Pythagorean theorem. The equation of a circle, of a unit circle centered at the origin, is x squared plus y squared is equal to 1, is equal to the radius squared. This distance right over here is equal to 1. Well, we've already said that we're defining cosine of theta as the x-coordinate of this point, and we're defining sine of theta as the y-coordinate of this point, and this point is sitting on the circle. It has to satisfy this relationship right over here. So that means, well, if we're defining cosine of theta to be the x, to be this x value, sine of theta to be the y value, and it has to satisfy this relationship, that means that cosine of theta squared plus sine squared of theta plus sine squared of theta needs to be equal to 1, or sine squared theta plus cosine squared of theta needs to be equal to 1. And that's just from the point. This is the x, cosine theta is the x coordinate, sine theta is the y coordinate. They have to satisfy this relationship which defines a circle. So cosine squared theta plus sine squared theta is 1. Now, this is called, as we've seen in other videos, this is called the Pythagorean identity. And you say, why is that useful? Well, using this, if you know sine of theta, you can figure out what cosine of theta is going to be, or vice versa. And if you know one of cosine of theta, and then you could, or say you know cosine theta, then you use this to figure out sine of theta, then you could figure out tangent of theta, because tangent of theta is just sine over cosine. But if you're a little bit confused as to why this is called the Pythagorean identity, well, it really just falls out of where even the equation of a circle even came from. If we look at this point right over here, which we're saying is the x-coordinate is cosine theta and the y-coordinate is sine of theta, what is the distance between that point and the origin? Well, to think about that, we can construct a right triangle. So this distance right over here, and so that we can deal with any quadrant, I'll make it the absolute value of the cosine theta is this distance right over here. And this distance right over here is the absolute value of the sine of theta. The absolute value of the sine of theta. And I obviously don't have to take the absolute value for this first quadrant here, but if I went into the other quadrants and I were to set up a similar right triangle, then the absolute value is at play. And so what do we know from the Pythagorean theorem? This is a right triangle here. The hypotenuse has length 1. So we know that this expression squared, the absolute value of cosine of theta squared, plus this expression squared, which is this length, plus the absolute value of the sine of theta squared needs to be equal to the length of the hypotenuse squared, which is the same thing, which is going to be equal to 1 squared. Or we could say, this is the same thing. If you're going to square something, the sign, if it's negative, it's going to be negative times a negative, so it's just going to be positive. So this is going to be the same thing as saying that the cosine squared theta plus sine squared theta is equal to 1. So once again, or I guess this is why it's called a Pythagorean identity. And actually, that's even where the equation of a circle comes from. It comes straight out of the Pythagorean theorem, where your hypotenuse is it has length 1.